Let's see what electric current is.
Imagine a super simple circuit. You've definitely drawn something like this in physics class. A battery, a switch, a light bulb. Now, picture the bulb sitting in front of you on a table, about a meter away from the switch. Nothing fancy. The interesting part starts when our two wires don't just connect the lamp to the power source directly, but instead we stretch them all the way to the two farthest points in Hungary. One wire goes all the way to Zahony, the other down to Ori St. Peter, and then both come back and connect them to the bulb. That's over 800 kilometers of cable, even though the bulb and its switch are still just a meter apart. Question's simple. If you press the switch now, when will the bulb light up?
It lights up.
If we go by what we learned in school, the answer seems pretty straightforward. We were taught that electricity works by electrons leaving the battery, traveling through the wire, and reaching the bulb. And if that's the case, then it should take a little time. Even if they move really fast, at least a round trip of 800 kilometers would cause a noticeable delay.
So as we learned, there are these little electrons wandering around in the wire, and then here they run out, or there are more of them, or at least that's how we learned it. Let's keep going. The video is almost correct, and I'll give a little correction, a little help about what we actually see from another perspective, okay? And this perspective I'm about to share doesn't reflect the current official scientific consensus, but if you try it out to see if it works, it will work. So there's definitely something sneaky going on here, something I think has been kept quiet for decades. Why? Well, that would take us way too far back to explain. But now this video is being made, so you can think about it, or even try it out for yourself. So what I'm saying is, when we transmit energy through a wire, it's primarily just information. And secondly, it's about positron flow, positron operation. So when you use only the positive pole and not the negative return pole as shown in the video, you're only operating with positrons. That's why I said this earlier, but you don't have to believe me. Just try it out, okay? Don't just take my word for it. I'm not saying you didactic one, this is some kind of concentrated nonsense. No, let's keep watching the video. So that's why I said earlier, people, and not just people, but all living things, operate with positrons. Because in our nervous system, there's no return branch either. There's only a one-way branch, a positive branch, which means positron, not electron. That's why, for example, in many cases, when a person is exposed to electric current, they can be revived, they can live again, and the electric current doesn't immediately knock them out, among other reasons. That's also why this phenomenon occurs. Just like there's also the phenomenon that basically, when living beings were tested with electricity, when they connected the positive and negative poles and the body started twitching, yes, that's caused by electrons. But with positrons, the organism would survive. This is the difference, and it's a huge difference. And the positron is in the opposite phase compared to the electron. So the positron is exactly in the opposite phase to the electron. Compared to that, let me say it again. I won't go into what this means because the video would get way too long, so let's move on.
Oh, it's not even detectable with the naked eye, but it can be measured precisely 2.67 milliseconds.
But
It doesn't matter anyway, because that's not what actually happens. In reality, the bulb lights up much faster than that, practically instantly, as if the length of the wire didn't matter at all. And you know what? It really doesn't. Not in the way you'd expect from what you learned in school physics class.
hold on. It's true. The length of the wire really doesn't matter. Do you know what this means? What about Ohm's law? That the performance you can observe depends on the material of the wire, its length, and all those squiggly details, right? Isn't that true? Isn't that what we learned? Ohm's laws and all those little things, resistance, inductance, and whatever else. So, what's up, guys, by the way? Everything okay? Because you figured something out, and that's great, and you're sharing it, and really, but still, what's the big deal now? You get it? The electric current appears instantly between the two poles. That's what happens, for crying out loud, because that's what direct current is, right? Between two poles, positive and negative, appear at once. What do quantum physicists usually call this? Electrospecialists. Quantum entanglement, my friend. Whenever a specific change begins from one single point of origin, let's say, for example, the initial signal, and then at both distinct locations, the positive and the negative, it always happens at exactly the same moment in time. Or, in the fascinating case of quantum entanglement, no matter how incredibly far apart those 2 points might be, the poles are always found to be perfectly opposite. One is positive, the other is negative. Now, when you really stop to think about it, that is a truly remarkable surprise. All right, let's keep going.
And this is an interesting problem because electricity doesn't work at all the way most of us imagine. The electrons in the system don't go anywhere, the current doesn't flow through the wire, so the question remains, why does the lamp light up? What actually happens when you flip the light switch, and why is all of this taught completely wrong in school? If we asked 10 people on the street how electricity works, we'd get pretty much the same answer from all of them. Of course, we'd find 10 people who would say that electricity works by electrons starting out somewhere, say from a power plant, traveling through the wires, entering your house, and then flowing into your devices, into the toaster, the hairdryer.
The lamp. There.
They use up their energy, maybe power an electric motor, or heat up a filament, or perhaps emit light, and that's the end of the story. This image is so deeply ingrained in our minds that we don't even notice how natural it feels to us. Electricity flows like water. There's a source, there's a pipe, The bigger the pipe, the more flows through it. If we shut it off, it stops. If it's longer, it takes more time to get there. Just like with plumbing. That's why the water pipe analogy works so well in
School.
You want to explain to a kid what electricity is? You just say, imagine the wire is a pipe and the electrons are the water. The battery or the power plant applies pressure, the electrons start moving, and the device works thanks to the energy of the water flowing through it.
This?
Just means yes, done. Everyone nods along. But the thing is, this image isn't simply the movement of electrons, that the energy travels inside the electrons, that the electron carries the energy from point A to point B, then releases it there, like a courier delivering a package across the city. This is a valid model. It really is. It's easy to imagine, easy to teach, and for most everyday problems, it doesn't cause any issues. But that's not what happens.
Really?
If electricity really worked this way, then in our previous example, the light bulb would have to wait. It would have to wait for the electrons to travel hundreds of kilometers back and forth. It would have to wait for it to physically reach it, but it doesn't wait. The bulb lights up instantly. And this is the point where this whole idea of an electron flow starts to fall apart, not because electrons aren't important, but because they're not the ones carrying the energy. The electrons really are there, they really do move, but their role isn't what we imagine it to be.
Ah, what does it mean to carry energy? So then the electron itself is an energy? What is energy? What does it mean to carry energy? So in themselves, I have a problem with these expressions, with technicians, with physicists. They've really gotten into the idea that electrons exist like this, and that we're talking about electronic energy. But I say it's just a kind of information that says there's electronic energy. So there's some kind of phenomenon of the universe, and I know this sounds really far out, but is it a property of the universe? Is it a characteristic of the universe that there's this kind of energy-like thing? But let me go a bit further, because the story gets more serious. And here
comes the first major contradiction. In the electrical grid, it's not direct current, but alternating current, as many people know. This means that the electrons don't travel in just one direction along the wire, but move back and forth, forward then back 50 times a second.
Tahir?
In other words, the electrons don't travel from the power plant to your house. They don't go all the way through the wire. They don't arrive at the outlet. They simply vibrate in place.
Damn it. They vibrate in place. Where did it get its kinetic energy from? That's my question. So, okay, I get that there's a coil, and in that coil, say in the case of a generator, electricity is induced and it starts to move. Where did it get its kinetic energy from? So how do you give it kinetic energy? Even if it's just vibrating, for example. What gives it its vibrational energy? What can transfer energy to something else if it itself is just energy? I don't know. Does what I said make sense? So whether it's oscillation like this in a tube, water, or an electron, or whatever you imagine inside, if you push it here, it moves there. What kind of energy process went through the whole thing? if, let's say, the whole thing is just energy. Now, you can imagine it however you want, what kind of energy it is, whether it's white or yellow or whatever color. What transfers the energy to this point like this? Energy? Does energy transfer the energy of energy? Time. Tick tock, time. It's just a change in time. But let's move on.
If we quantify this, the picture gets even wilder. The so-called drift velocity of electrons, meaning the speed at which they move on average in one direction, is about a tenth of a millimeter per second. This means that in 1 second, an electron moves about as far as the thickness of a hair.
So,
The electrons working in your imaginary lamp didn't come from far away. They didn't arrive from the power plant. They didn't travel across the country. Chances are they were already in the wire hours, days, or even years ago. They just started oscillating back and forth now. It's worth pausing here for a moment because a few reasonable questions come up at this point. Okay, there's alternating current in the outlet. The electrons move back and forth, but most devices don't actually work like that. Phones, laptops, and TVs all use direct current. So could it be that alternating current is just for transmission and the actual operation happens with direct current? With electrons flowing in one direction, like we learned? Not really. The thing is, as the name suggests, direct current does want a one-way movement, but the electrons aren't zipping around at the speed of light. Instead, there's just a very tiny average displacement. With alternating current, it's similar, just a fraction of a millimeter per second. It is impossibly slow, so it still doesn't transfer energy to the movement of electrons.
oh,
It's just not this electricity, so
yes.
if you stick with me for the next few minutes, you'll understand this phenomenon for life. Let's dive in. An atom has a center, and around it there are tiny, tiny particles orbiting. These are called electrons.
There aren't actually particles orbiting. There aren't any particles at all, like little parts of something circling around. They're in a state of superposition. That's what I'm saying from another perspective. Let's stick to this perspective so we can understand what we're talking about, because it's not a particle. So that's a bit of a misrepresentation. The principle isn't bad, but it's misleading. They're in a state of superposition. They're always in n places at once, and the density always collapses into the position where we're observing it. So, specifically, where you interact with that space. It condenses into that point, and that's when, as quantum physicists say, then feel free to interrupt me if I'm wrong, but this is when we say that the wave function collapses. And at this point, out of the n possible positions, there could even be infinitely many n's, by the way. The specific position is realized. Let's call it a condensation-like phenomenon. If you imagine an energy cloud in one of those n positions, if you imagine an energy field, there aren't any particles in it, just wave functions and more wave functions, processes in space-time. Then in reality, it just condenses there. It concentrates there. That's where the event horizon falls in. How could I explain this in an even more understandable way for physicists? If the dear viewer has lost track, I apologize in advance, but this is how it's going to be in this video, so that whoever made this video understands what I'm talking about. So, well, maybe it can be used for something. For example, we have wave genetics, matrices. These are just audio files. And wouldn't you know it, sounds are always longitudinal waves, longitudinal scalar waves. Scalar sound waves work in a kind of shock wave-like way, and the matrices of biological patterns are encoded into these. You just have to listen to them 2 times 30 minutes a day, half an hour each time. You can find them on the lif.academy website. So, if you think what I'm talking about is nonsense, then let's have a serious conversation now, and let's really try to understand what this is about, because they also feel that there's some kind of problem. I can see that. But I'll tell you what the problem is, based on a few decades of experience, not just mine, but I work in research and development in this field, okay? A couple of things have seemed a bit strange to me too. Just a little bit. Not much, just a little. You can see this in my videos. And actually, you can do these experiments at home. You can repeat them. I work in research and development, okay? For research labs, it should actually be mandatory. Now, let's keep watching the video.
Electrons have an important property, namely that they are negatively charged. For now, this is just a headline. Don't look for any deeper meaning.
Behind it, Just that.
That electrons are negative.
It's not really negative and not really positive either. Its polarization is different. I'm looking at it from a quantum physics perspective. It's not truly positive and not truly negative. It's a matter of phase and polarization difference. That's it. That's all that's happening.
There are materials where these electrons are very tightly bound to the atom, and there are others where they can move a bit more freely.
So, does it have a smaller field or a larger field?
This is a very important property, and that's why, due to their conductivity, wires are.
Metal. And
Imagine the wire not as a tube, but as a solid material, filled.
with electrons.
In reality, the inside of the wire is like people sitting in the stands of a stadium. Every seat is taken. No one can just run around. They can't. When the wire isn't connected to anything, everything is calm. Everyone is sitting in their place. Of course, everything has a basic vibration, but it's just in place. There's no direction, no purpose. Electrons are negative, so where there are more of them, a negative charge is created. A negative excess, if that makes it clearer. Where there are fewer electrons, because of the positive nature of the atomic nuclei, a positive charge appears. But why is this important? Because when you connect a power source to a system, that's exactly what it does. You take electrons from one side and pile electrons onto the other. It doesn't send electrons around in a loop, it just separates them, always locally.
It doesn't separate any electrons. Just think about it. This isn't right again. It's not right. It's simply not right. How could it separate the electrons, whether locally or however, if we're talking about, say, a 1 kilometer long wire? How long would the separation time be? How long would it take along the entire length of the wire? Uniformly, equally, they have to be distributed and separated completely uniformly for that thing you're talking about to work. Simple logic.
On the surface of the wire, there will be a bit more electrons in some places, a bit less in others, and this difference is what we call voltage.
No, voltage is always created by a potential difference. Without a difference in potential, in other words, without any variation in potential, there is no voltage. So, potential. Potential. Not some kind of, I don't know what of arrangement. Although we could call it the I don't know what of arrangement, but then we'd have to call it entropy. That's what arrangement is. Order is syntropy, and disorder is entropy. And that's how we can talk about it. Because then, in terms of entropy, decrease, so the centropic in this sense is negative entropy. Centropic increase determines the magnitude of the potential difference. Is that it? Is that all?
Not movement, but difference.
Yes.
Difference. We could say imbalance, and this is what creates electric current. Here comes the first thing that school.
Electric current. He knows we aren't really talking about current, so let's get into it.
A completely subtle and invisible visual effect suddenly begins to manifest itself on the screen, and this is the specific phenomenon we're observing right now.
An electric field? Well, I'd rather say it's the actual change. This is another complete misrepresentation of the facts. This is yet another fundamental misrepresentation. So, what specific kind of electric field exactly appears if the potential is high? Why does the electric field appear? What is the electric field? What is the electric field? If the electron is already present in everything, then what is the electric field? If, just an idea, anyone? I say that at this point, when you say electric field, that's when the quantum physical effect is created, which is being prepared. To put in more precise terms, it establishes the foundation for the basic phenomenon of quantum entanglement. From that point on, quantum entanglement is already capable of functioning, which means the poles will steadily and progressively take shape over time.
The electric field is not an object, not a material, but rather the way space responds to there being more electrons in one place and fewer in another.
Space-time? Space-time. Physicists, space-time. Uncle Einstein, the almighty for you guys, also says some good things. But listen, there is no space without time and no time without space. Space-time, space-time, space-time.
Space itself senses that there is no balance. This electric field is what can act on the electrons. This is the next step. When this electric field is present in a conductor, then the electron's there. The field itself also forces the charges. Oh boy. So
When the electric field is present, it forces the charges. And what's going on here in Gionios? What is the electric field, and then what is the electron? So the electric field is the quantized version of the electron, because there are no particles there anymore. So first, you're looking at quantum phenomena, and second, you're examining, then you jump back to some kind of knotted state, and you say that this is a material type particle. You keep switching levels, mixing things up, and then sometimes you say this, sometimes you say that. Hasn't this occurred to you before? Well, we're watching. He hasn't noticed, and I don't want to pick on him because at least he's thinking, and he's thinking differently than the others. You can see that, but it should be done a bit better.
the electrons start to react to this effect, and that's how what we call current is formed. So current is nothing more than the movement of charges under the influence of an electric field.
Phew, phew. No, sorry, no. When there's a potential difference, we do work in an electric field. When there's a potential difference, we do work in an electric field. This is electric current.
So it's not the movement of electrons, that's the key. The electrons don't travel all the way through the wire like water in a pipe. They don't go from one end to the other. What happens is more of a rearrangement than a journey. The electrons are already present everywhere in the wire.
Yeah.
When a charge difference is created by the power source, these electrons react locally. They shift a little, then again and again, while constantly colliding with the atoms of the material. So in reality, it's not a stream of electrons flowing through the wire, but rather the distribution of charges that changes, along with the whole system. There is
Charge, there are no little balls, no little beads. For heaven's sake, you are the one who explained how things work around atoms, so what little beads are we thinking of again now?
at the same time, and that's the key word, at the same time. This is the
The key word is at the same time. This is called quantum entanglement. Come on, let's go, wake up, rise and shine.
This happens simultaneously. But just to finish the train of thought I started, moving charges also create another effect around themselves, and that's the magnetic field. Let's pause.
Let's stop for a moment. What is a magnetic field? I don't even want to say the word because you'll lose your minds and drop your belts if you haven't already. But what is a magnetic field? A simple example. We have our favorite type of magnet, neodymium. It's a rare earth magnet, right? What material is it made of? The neodymium rare earth magnet is made from a material that originally wasn't magnetic. What makes it magnetic? It becomes magnetic when we put it under pressure and give it energy over a longer period of time. What changes between the two states besides its magnetism? The most important thing, the absolutely most important thing, the K factor, the time factor changes. In other words, in Hungarian, even before the magnet became a magnet, its decay time was fast, it decayed quickly, it had a short half-life, it broke down quickly, it degraded faster, it wore out faster, much faster, even before or even after we did the compression hocus pocus and it became a neodymium magnet. Because in the case of a neodymium magnet, the K factor, the decay time, is already slow. It's almost frozen in time. And when it's frozen in time, these very nice lines appear around it, let's say. In the case of a toroidal magnet, which we call magnetic field lines. Now, these magnetic field lines, now you might understand where they come from, maybe, the K factor and little details. You see, it's just the time difference that created them, and energy. Well, anyway, that appears in this case too. That's how magnetism appears. Among other things, as a result of condensation. Magnetism as a result of condensation, and a kind of energy, whatever, as a result of energy passing through, as a result of energy information passing through.
These things are interconnected. If there is an electric field and it moves charges, then a magnetic field also appears around the moving charges.
A magnetic field also appears around moving charges. Well, if I take, say, a piece of plastic, there are electrons in that too. or a wooden block and I spin it, then will there be magnetic fields around it? Will there be a magnetic field around it? What's around it isn't really a magnetic field, actually. Do you get what I mean? Since when is a wooden block magnetic? There's a lot of metal in it, right? But
That's why it's called electromagnetism, because the two phenomena are connected. The main point, in short, is that a difference in charge generates an electric field, and the movement of charges,
a significant difference in electrical charge subsequently generates a potential difference, and as a result,
that in turn creates a magnetic field. But a changing magnetic field in turn generates an electric field, and so on.
this isn't necessarily always true. This is misleading again. It's not like that. No, wrong. No. Because if you have a wire, you connect, I don't know, something to it, you drive it with a frequency generator using a square wave at 1 megahertz. Then only one pole is used, and then the shock waves travel through it. Or at least, as the signal passes through it, the frequency generator drives it at 1 megahertz. But if you put an Averman coupler at the end, a BAV76 diode, twisted together with a cathode and a LED on it, the LED will light up in your hand because the positrons have passed through it, and as the positrons pass through, they meet this part of the Averman coupler. The positrons start moving in both directions, but the P-N layer in the diode transforms and conjugates these waves. This is how phase conjugation is created, or phase conjugation. Phase conjugation already produces negative entropy phenomena, centropic phenomena. Many people think that negative entropy means we're talking about negative things, and so you have to be sad about it. No, because entropy is exactly what's bad, and that's what we live in. So everything that is physical, that has physical properties, all of it has entropy. Not negative entropy, all of it has entropy. It shows a divergent effect and breaks down. And it gets ruined. Only negative entropy holds it together. Information, that information which is ordered. Because if it weren't ordered, then everything would have fallen apart. And with heat death, everything would have ended a long time ago. Everything would have decomposed. Everything would have turned into heat. And we would have said goodbye. We wouldn't be having this conversation right now. If negative entropy and centropy didn't exist. So, in other words, a reverse timeline. A kind of reverse timeline that shows coherence, holds everything together, and organizes everything. It holds everything together and keeps everything unified. And it has a source point, not in the sense of being hot, but it has a source point in terms of where it originates from. That's how it has a source point. Where does it come from? What is its origin? I've gone very far afield, so let's keep going.
Back and forth to infinity. Their relationship is two-way, so it's a kind of feedback loop, a circular system. They create each other and sustain each other.
If you create a closed system and think in closed loops, then yes. But nature has always been an open system, and nature thinks in open things. Simply because closed systems always feed back on themselves, and eventually they break down. They break down, that's the right word. It's not that something comes from somewhere and then breaks down. Open systems are living systems. Let me say it again, more slowly. Open systems are always living systems. Well, if life was already there, then yes. If not, then no.
This is current itself. From here, the picture comes together. The power source creates a difference in charge. The
difference in charge creates an electric.
The electric field sets the charges in motion, and the moving charges generate a magnetic field, but
isn't it suspicious? 900? Are you showing a 90-degree difference? Take a look. These blue rings are at a 90-degree angle compared to the wire. Isn't that suspicious? Isn't it suspicious that we're actually talking about shock waves in the wire? So when you set up both POUs at the same time, or you add the circuit, or you put the little thing or the battery onto the device, you've already created a shock wave on both wires at the same time. You turn it on, you switch it, and even then it's a single shock wave, a single piece of information. It's basically just for it. Potential difference? The AB poles are already there. The potential between the AB poles of the battery is already present, and it's there, yeah. So what? What you drew there is a 900-degree deviation. That's a shock wave. A scalar shock wave is a spherical shock wave. It's very simple. You can check that what I'm talking about actually exists. You take any oscilloscope, plug the extension cord into the 220 or 240 volt network, step on it with 1 foot, the shock wave passes through you, you hold the oscilloscope in your hand, and you can see the voltage difference on it. And the frequency will match the network frequency no matter what. You stepped on a plastic cable with insulated shoes, which is just plugged into the wall. So this isn't capacitive coupling, and I'm not grounding anything with this. That's all I'm trying to say. Yeah, whew, I just scarfed down a nice kebab, so let's keep going with things here.
And when electric and magnetic fields are present at the same time, according to physics, energy starts to flow through space. When
Electric and magnetic fields are present simultaneously. From my point of view, that's what I call turbulence. That's a shock wave turbulence, and it's the turbulent flows that create magnetism in it. If you remove the turbulence, then a part doesn't flow back. It's much more efficient, of course, much more usable, and not harmful to biological organisms. If you remove the turbulence, it's just that it doesn't have that name anymore. And let's say you even invert it, so to speak. Then we're talking about radiant energy, and that's already an entropic effect, but we're not there yet. Let's keep going.
not in the wire, not in the electrons, but around them. That's why it's important to understand that the movement of electrons isn't the first step, but rather a consequence. First, there's a difference in charge, which creates an electric field, and only after that can we talk about the flow of electrons. Ultimately, the movement of electrons produces heat and light, but electricity itself is a physical state.
Both thermal heat and visible light are produced because of the rapid movement of subatomic electrons. No, it is actually primarily due to the effect of the significant change in their overall energy levels. And because of the effect of the time difference and informational phenomena, this happens. But it's not because something bumps into something else and then it gets hot or whatever the idea is. What does it even mean that heat is produced? That's my problem. What is it? What is it doing? What exactly is it? We just throw in another property like that. Look, it's like saying we're making a little soup and then once the soup is already completely finished and done, we just throw in a little something else or whatever. You know exactly what I'm talking about. And then you use that specific thing to explain everything else. You see, there are some very deep and fundamental definition problems in the field of electronics, and honestly, in the world of mathematics too.
Oh man, I've been thinking so much more about that specific idea I brought up to you the other day. And honestly, the more I dwell on it, the more I realize just how much potential it actually has for us if we really take the time to sit down and develop it properly into something substantial and meaningful for the whole team to work on together.
That works. This idea, well, it's just an idea. Let's leave it at that.
Those tiny differences in charge that created the electric field disappear, and if there's no electromagnetic field, then there's no flow of energy either. Going back to our original thought experiment, that's why it's not the length of the wire that determines when the bulb reacts, even if the wire were to go all the way around the Earth. The delay in switching on the lamp doesn't depend on how much wire you lay out, but only on the distance between the switch and the bulb. Um,
OM rules. OM rules. Ohm, right? Nobody misses those. So, like, and then there's induction and all that stuff. The things we got used to. Nobody misses those rules. So now there's a new explanation when it's wrong. So, in absolute terms, I extend the energy of the single conductor so that no explanation at all. Nothing. Zero. Zilch. You see that it exists. It does. For example, if you buy a xenon tube, you can see it exists because the xenon sparks back. And if you cover it, say with iron oxide, then you add another layer of electrical insulation, I don't know, PVC or whatever. PVC works too, but let's say you use, what's that stuff they use in pancake pans? Teflon. You put Teflon on it, so you insulate it with everything. As I already did this experiment 2 years ago, the energy still passes through it. I apologize. And the potential difference appears immediately. So, again, Ohm's law, thermodynamics. So, okay, this is another perspective. But then negative entropy, centropy, that is, centropy meaning an ordering principle. In other words, the opposite of what is here. We experience, I'll say it slowly for everyone, you have to introduce that. Without it, this is just a damn big mess. This is a mess as it is.
As long as these are next to each other, after the switch flips, the current appears in the bulb at the speed of light. At a distance of 1 meter, that's 3.3 nanoseconds. From the moment the power source is connected to the circuit, it continuously maintains the charge differences and the electric field. So what is the point of the switch? It is there to close the circuit, and this, its working definition, is not like that. Rather,
Yes, that is exactly what happens when we do work within an electric field due to a potential difference. The noted figure, Harry Meyer, described the situation in this specific way. You're welcome. The water-powered electric car's inventor. Now, let us move on to the next topic.
the circuit, one side of the switch was perhaps already there's a positive charge present, the other is slightly negative, and as these come into contact, finally the movement of the particles can begin. The state of the electric field changes locally, and the effect of this change propagates at the speed of light along the circuit and in the space around the conductor. Electrons still do not arrive at the bulb's term.
No, 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 that's not right. That's not right. Do you know why it's not right? Imagine you have a wire so big, or you wrap it all the way around the Earth like this, all the way around, along the equator. There's the Earth, like this, a sphere, not flat, a sphere. Here it is, a geoid, to be even more precise. We wrap it all the way around with a wire like this, we turn it on, and then you say that the electric field travels at the speed of light because what? Maybe around the wire. So that means if I put a pencil battery on the wire like this, click, then all around the whole globe like this on the sphere, everywhere, this kind of electric current starts to spread. So it will spread inside it like that. And when it has already spread, then the lamp or whatever will turn on here. Seriously? Is that really how it all works? I'm honestly not trying to be rude at all, but it just suddenly struck me that something about this whole situation doesn't quite add up for me. Is there perhaps a clear physical example you could use to explain this better? I mean, I've personally never seen a specific example quite like this one before, even though I know people talk about it all the time. But listen, that is exactly how it is, right?
Dude, that would take hours. The light bulb simply enters a new electromagnetic field state, and in this state, it starts to absorb energy.
Electromagnetic field state. In the case of direct current, the light bulb enters an electromagnetic field state. Now, I don't know, is this the old theory, the newer theory, or what the heck is this?
The movement of the free electrons does work, and that's why it starts to light up. That's why the concept of current flow is misleading. The word we call current is not something that moves, but rather a maintained state, a balance between the electric field and the arrangement of charges.
It's the balance between the electric field and the arrangement of charges. That was a nice sentence. Yes, that's what it's about. The balance between the electric field and the arrangement of charges. Balance, potential, difference, deviation. We do work in the electric field. This will be good. This will be good. We just need to focus. Guys, focus, focus. Not coconut. The coconut is in the soup. Focus. This is focus. Not a TV channel, not media, not any of that. Like this. Focus. Concentrate on it. Concentrate hard. I'm telling you now. Put your hand here on the card.
Was able to transmit energy. If this just sounded complicated, and that's why you've never really understood what's actually happening with electricity, it's not your fault. These concepts are difficult, even for physicists. They weren't self-evident even for them. They argued about these things for decades. People who dedicated their entire lives to this. And the irony of it all is that by the time we started to understand this picture, electric grids had already been working for a long time.
How badly, for crying out loud. At first, they used direct current, and then everywhere you needed these huge transformer stations to convert it so the losses wouldn't be so big. Basically, they couldn't transmit energy over long distances with direct current because that was the limitation. I think it was Westinghouse lately who was involved. They started arguing about it, which one would be better. And in the end, it was Tesla's alternating current that spread, precisely because it could be transmitted over longer distances. These alternating phases. Alternating phases, okay, you can transmit this over a larger area because of the variation. Not because it's better, not because it's stronger, but because you can maintain that system more reliably, the one you're paying your small change for. It can be maintained more reliably and works over greater distances. Let me say it again about the system. The more changes you apply, so for example, if the frequency were higher, which is still somewhat related to the voltage in this form, then it could operate over even greater distances. This is how power transmission networks work, for example. Those operate at even higher frequencies, with even higher voltages, and with even greater potential differences. In a lot of groups, it comes up. Claims that the systems are already providing free energy and that we're just being tricked, and that we're actually generating electricity for the power grid completely for free. That's not true. That's not true because there are normal entropic networks. That means there are losses in it, and not small ones. Plus, the system needs maintenance since poles fall over. The actual cost of maintaining everything is a separate topic, because that's not certain that what they're putting together there is correct, but that's not my business, because it's probably not your business either. So let's just leave it at that for now. What is my business is to try to interpret this video and to share the knowledge and ideas that, as you can see in the videos, make the signal transmission work for me. This and that. What is the perspective I approach it from? And what is the perspective that official science presents? Nowadays, in a somewhat revised, rethought version, but still not quite correct. I have to say, unfortunately, it's not correct. It's not correct, guys. Let's keep watching the video. I'm talking too much.
There were lights, trams were running, the streets were lit up, even though no one really knew yet what was actually carrying the energy. We used it first and only understood it afterwards. Until the middle of the 19th century, people tried to imagine electricity as some kind of fluid, something that flows, moves, migrates from one place to another. This seemed logical because all our previous experience told us that if something carries energy, then it has to move. It has to go somewhere. This idea worked just fine until they tried to put this story to the test with a brutal worldwide project. In the 1850s, the idea came up to connect Europe and America with a telegraph line, so that letters wouldn't have to wait on ships for days or weeks, but messages could be sent almost instantly. The only thing missing was a tiny detail, a cable several thousand kilometers long laid on the ocean floor. But hey, hats off, the engineers pulled it off. In 1858, the first transatlantic telegraph cable was laid. Celebration, ribbon cutting, a historic moment. Then reality set in. The cable technically worked, but it was basically useless. The signals didn't go through the way they were supposed to. Telegraph Morse signals are basically simple, right? Dots and dashes, short and long pulses. The problem was that on such a long cable, the pulses started to smear out. Short ones became long ones got even longer, the signals overlapped and got distorted. It was like someone trying to draw dots with a pen, but the ink would smear after every dot, and by the time, compared to the plan, it slowed down to just a few words per minute, and even that was full of errors. In short, the grand dream of instant messaging collapsed as soon as it was realized. But the burning question remained: why did this happen? The scientific war broke out, not with weapons, but with metaphors. One side said it was just like water flowing through a pipe. The signal flows in, then somehow makes its way through. If it gets distorted, then it must be leaking or stretching, or there's resistance somewhere, or it's just moving too slowly. One of the most well-known figures on this side was William Tom Zom, who later became known to history as Lord Kelvin. He really imagined that the behavior of the electric signal could be compared to water flowing through an elastic tube. But then there was another camp who said, guys, you're looking for the phenomenon in the wrong place. You don't need to understand what's happening inside the wire, but around the wire, because the cable isn't just a partial conductor. There's insulation around it, there's the medium it lies in, and there are the fields. And if these fields behave in a way that smears the signal,
What do you mean, the fields? Like cows grazing out there? It might be, but honestly, if we were talking about quantum physics, then I'd say yeah.
so it really doesn't matter how perfectly you polish the inside of the wire. It's still going to get distorted because the system isn't just a tube, it's a whole electromagnetic system. That's when it really started to make sense.
It's not electromagnetic, because when nothing's running through it, what attracts the fish? Or what does it even do there? You get it? There's your wire with insulation on it, and that's it. We didn't put any electrodes in, we didn't connect anything, nothing. So what makes it electromagnetic there? Why? Why then is wood electromagnetic too? Come on, everything's electromagnetic. I know, because ever since Marconi, since electromagnetism was discovered, now everything is electromagnetic. But nature doesn't work like that. That's the problem. We can see this. So people who live near transformer stations, unfortunately, many of them get cancer, get sick. I can't even talk. Get sick. That's a tough word. Because with these waves, they encounter numbers that carry the information of the transformer station. And this happens in the form of a kind of turbulent flow, which spreads out, radiates into the transformer's flow. And people get hit directly with the information from the iron core and all sorts of junk that the station is built from in a turbulent form, making it even worse.
So it gets even worse. So the
In the leafy force, I just want to say that radiant energy, that is the centropic energy. That's something very, very pure. That's pure energy. But if you use it in a turbulent form, you cause massive damage. So actually, electromagnetism as we use it today, whether it's a cell phone, a transmission tower, or whatever, it doesn't matter. It's very harmful. Much more harmful than actually the kind of energy Nikola Tesla might have come up with. That was a good idea. But as far as I know from the story, Murray, no, not Murray, Murray was his partner. He repeated the experiment several times, but not Meyer. Who was that guy who withdrew his support? Because the point was there was the Wardenclyffe Tower with which he could deliver the required output, not electromagnetic output, but energy output, and everyone could have a small device at home to use this energy. This was Tesla's basic concept, Tesla's idea, but his partner primarily wanted to use it for information transmission, especially back then, because as mentioned in the video, these problems came up. Yes, there were issues with the cables and they couldn't explain or solve them, and they struggled with it a lot, etc., etc. Meanwhile, there was Tesla's idea, which didn't work with electromagnetism, but with energy pulse waves, a pretty big difference, and moreover, with inverse energy pulse waves. And actually, the same phenomenon applies to it as to the electricity discussed here. So, if we look at electricity according to the standard model, Tesla's principle, his ideas, can be traced back to the standard model. You can convert between the two at any time. Based on what I've said, and really, especially if you look into it, or try it out yourself with a simple little plasma globe, the kind you can get as a toy, just wrap an insulated wire around it, and you connect a small LED to one end, and to the other end you attach an aluminum plate. On the aluminum plate, you'll see the effect of charge being drawn away. So your positron travels along a single wire, well, not exactly travels, but there's a kind of positive energy shockwave change happening there, and it gets conjugated in the metal plate. So the backflow happens in the metal plate. The shockwave goes into the metal plate, reflects back from the metal plate, and that creates a field. Actually, it already has a field to begin with, because it occupies all space and time, so it inherently has its own field. From a quantum physics perspective, this is even more true, but the point is that within that little plate itself, as the vortex current, let's call it that, forms according to the Eliasberg order, a suction effect appears, and this suction effect is nothing other than the metaphysical manifestation of what could even be called the creator, because an energy flows across this metal plate at a 90-degree angle in such a way that if it is raised, if we assume that everything moves forward in time, then it moves from the future toward the past, and the metal plate is the present point. That's how the energy flows through it. That's just how it is. And that's how it creates a suction effect. There's a lot more that could be said about this, but let's continue with the video. The video is almost over, and so is this part. If what I said was too much, but it's worth thinking about. So I'm not saying this because I want anything bad. Not at all. It's simply because I see that this is how it works. And many people who watch my videos, many have already tried it out and seen that it works this way. Even 4 of my acquaintances have tested it extensively with large Tesla coils, and it works like this. Everyone has a slightly different perspective. Just a little different, not very different. And that's an important thing, that the perspective isn't very different. The perspective is a little different. It's a bit different how we try to explain the same phenomena, but nothing is being read into it. And the first thing is that these are repeatable phenomena. And if we discover something that could make humanity's fate better, then we should use those things, right? I mean, if that's the goal. And here, in the end, it always comes down to what kind of inner anchor someone has. This is very important. What kind of inner anchor they have and what decisions they make based on that anchor, while taking into account. I often find myself wondering exactly how life could have possibly come about in this vast universe. To be honest, I really don't know where this line of thinking will eventually lead us, so it's not just a simple matter. The specific kind of person someone becomes and the complex decisions they make every single day will always fundamentally depend on what specific values you hold most important deep down inside your heart. That's the only thing that changes your perspective. Your perspective changes depending on what values you hold important inside. And can you adjust your perspective? Do you even have an internal anchor? Or do you just swallow whatever anyone tells you without trying it out first? If you just swallow it right away, then you don't have an internal anchor. You should have one. But try it out. See for yourself. You can't do this without experience. Sure, you can talk about these things without experience, but it's the experience that makes you absolutely certain you're right. And no matter what anyone tells you, you still know you're right. Let Uncle Pista talk a bit too. He's almost been at this level before. But just so you get what I'm talking about, I tried to explain it to you this way. And like I said, if you try this little thing now, you'll see for yourself. Well, you to see for yourself, my friend. This is how it is. It's really hard to misinterpret this. We measured it in several ways. For example, with a multi-axis spectrum analyzer, among other things. With this, you can specifically select whether to look only at the electric field, only at the magnetic field, or at the electromagnetic field, and you can examine it in 3 dimensions. So that's why the spectrum analyzer is multi-axis, because it can measure the fields from multiple directions. And in this case, the magnetic sea was not present. It is present in a special version when the magnetic sea is included. Magnetism also tells us that when you have that field and you move the probe within it, then there is magnetism present. In that case, you end up creating turbulence around it, so the thing senses a magnetic field, but otherwise there is no magnetism in it. As long as you are just using the field of this phenomenon, there is nothing magnetic in it at all. There is order in it, sure, but that's not magnetism. Magnetism begins when you close this energy into a loop, into a ring. And then, being closed in on itself, it spins for quite a long time and maintains the ordered state of energy, which is what you call magnetism. And that also has an additional field, right? I don't want to go too deep into these little loops because it might be unnecessary. The 1960s.
In the 1970s, the work of James Clerk Maxwell was a huge breakthrough. He was the one who mathematically demonstrated that light is not some mystical substance, but rather the oscillation of electric and magnetic fields. In other words, there's an electric field, there's a magnetic field, and together they can propagate like a wave.
Yeah, sure. So if I put a horseshoe magnet there, then the light will turn. Or can I, for example, separate light into its electric and magnetic components? If you say that I can split light into electric and magnetic components, then I can manipulate them and then later combine them back into light again. Because it doesn't work like that. I'm just saying, that's not how it is. What kind of explanation is that? You say electric and electric and electromagnetic, and that's light. Why isn't there an application for this, like this? Let's see how much magnetism is actually present in light. This isn't the photovoltaic effect, okay? This isn't how a solar panel works. That's a quantum physics process, how a solar panel operates.
This alone was already shocking, but what's really important about the cable is that from this point on, more and more people started to think that when something happens in a wire, something is also happening in the space around the wire. And it was a mistake to leave this out of the equation. Because with the transatlantic cable, this was the trap. The cable was designed with a copper conductor in the center, insulation around it, and then an iron sheath on the outside, which was needed for protection, to keep it from breaking, to withstand the sea, to keep great white sharks from biting through it, and so on. But the thing is, iron itself is also a good conductor, and this cable, this affected how the fields formed inside and around the cable. The outer sheath influenced the signal running through the wire inside. Specifically, whenever an electrical signal appeared, the iron sheath would slightly hold back the signal everywhere. It didn't stop it, it didn't absorb it, it just delayed it, just for a moment, and then it let it through. Only,
There is actually a very good and clear example for this, which is a bit simpler to understand, but the underlying phenomenon is quite similar, especially when you have a long, hollow copper pipe. And if you drop a magnet inside, the magnet won't just fall straight through the copper pipe, but instead it will slowly descend. The same phenomenon happened here with the cable. When you let the magnet go, eddy currents form in the copper pipe as the magnet moves. So the movement, the motion of the magnet relative to the copper, creates these eddy currents. And these eddy currents act in opposition to the effect of the magnet. Compared to the force exerted, it slows down the fall of the magnet a bit. The magnet goes down slowly inside the copper pipe. In the case of Tatingroddy's experiment, something similar happened, because here, even though it wasn't copper, but rather an iron shell that surrounded the signal, which would have otherwise traveled in pulses continuously, but then why would they use an iron shell? Anyway, these are some of the interesting details.
when this happens over and over again across thousands of kilometers, the effect adds up. So the short pulses didn't stay sharp, they got smeared out by the time they arrived. The long signals became even longer, and the boundaries got completely blurred. So the difference between a dot and a dash slowly disappeared. At this point, the era of fields arrived in engineering practice as well. It wasn't enough to just say there was voltage and current. It was necessary to understand that the propagation of the signal doesn't depend only on the wire, but also on what kind of electromagnetic field the wire creates around itself, and how that field stores and transfers energy, and how it deforms the... So a bad mental model isn't just a minor misunderstanding. A bad mental model can ruin thousands of kilometers of cable, the dream project of an entire era, and the communication of half the world. Not because the electrons somehow got stuck, but because they didn't understand that the key isn't in the wire itself, but in the space around the wire. This also helps us understand something we all see, but maybe never really thought about. Look up next to any country road. High voltage power lines never run underground or inside pipes along walls, but instead they hang out there in the open air. Way up high, often on poles that seem unnecessarily tall. At first glance, this seems strange, since air doesn't conduct electricity, but the ground does. So why don't we put them closer to the ground? Why don't I protect the cables there? Well, it's exactly because the wire itself isn't the main thing. The electric and magnetic fields that form around the wire need space. If it's too close to the ground or too close to another conductor, then this field releases energy where it shouldn't. From that point on, everything gets distorted.
Due to the effect of potential difference. In an electric field, we do work. There's a connection between potential difference in the electric field because work is also related to it. In this sentence, as I'm saying it now.
It gets lost, it becomes noisy. The same thing happens on a small scale as what happened with the transatlantic cable on a large scale. Air is ideal for this because it doesn't interfere. It allows the electromagnetic field to form exactly as the system needs it, since the conductor itself, you see, doesn't carry energy. It just defines the path of the electromagnetic field. And this brings us to the question that's been hanging around us since the beginning of the video. If this is so fundamental, if it so strongly determines how this whole electric world works, then why don't we learn it this way in school? The answer isn't that it's taught wrong, but that it has to be simplified. Because the model we've just gone through, the fields, the charges, the energy distribution, even physicists took decades to really piece it all together. In fact, for me, it took a long time to be able to explain it well myself. So it's really not that simple at all. You can't explain this to a sixth grader, and honestly, often not even to a high schooler, without them getting completely lost in it. That's why the water pipe model, the story of electrons flowing, has survived. Not because it's true, but because it's useful. It helps you understand what a switch is, why a light bulb lights up, and why a fuse blows. For 90% of everyday problems, that's enough. But of course, every simplification comes with a price. If we carry this model with us for too long, we start to believe that this is reality, that flows, and the energy travels in the electrons. And when we first encounter a situation where this doesn't work, like with a long wire, we have to realize that we've learned a simplified version. Oh, before I forget, let's also clear up this direct current versus alternating current thing in just half a minute, because at the beginning everything was so confusing, but now you understand the main point better. When I explained current, I cheated a bit by using alternating current to show what happens. In both cases, the basic principle is the same. The movement of charges generates the field. The difference between direct current and alternating current lies in how the electric field behaves over time. With direct current, the power source creates a charge difference and continuously maintains this difference. Because of this, an electric field forms around the wire, which has a specific direction and magnitude, and this does not change over time. It's as if this field settles into a certain state, and as long as the power source is operating, this state is maintained. In this case, energy transfer happens in such a way that the stable electric field continuously acts on the load, transferring energy to the material of the load, generating heat, producing light, or doing work. With alternating current, however, the power source does not maintain a constant charge difference, but instead continuously changes it. Because of this, the electric field is not constant either. Its direction and magnitude change periodically over time, 50 times per second, which is 50 hertz. It reverses back and forth, and this is where the crucial difference comes in. A time-varying electric field automatically creates a magnetic field. This isn't optional. It's a law of physics. With alternating current, the electric and magnetic fields generate each other, coexist to form an electromagnetic system. Is this alternating electromagnetic field that carries the energy from the source to the consumer. And I hope you remember, it's not inside the wire, but in the space around the wire. In this case, the consumer draws energy from this alternating field. In both cases, energy transfer happens through space. The only real difference is that in one case, the field is quietly present, while in the other, it pulses. So, to sum up the past 20 minutes, the lamp lights up because the power source stores energy. This energy is transmitted by an electromagnetic field, regardless of whether it's constant or alternating. In the material of the bulb, this field does work, transferring the energy from the power source to the atoms of the bulb, which then appears as heat and light. So electric current is not a flow of electrons, but rather the invisible work of an electric field in the space around the wire. I hope you found this video interesting, and if you're curious about another often misunderstood physical phenomenon, click on the one shown on the screen.
Actually, I found it quite fascinating.
The video, thanks. I hope
That you all found this video interesting too. Bye. Oh, wait, before I go, lif.academy. There's a little explanation about this there, okay? Bye.